Welcome back to our deep dive into the Fukushima Daiichi accident.
Yeah.
Last time, we really dug into that immediate response at the plant as things were happening.
Right.
Today, though, we're going to kind of shift gears a bit
Okay.
and look more at the, I guess you could say, the aftermath.
Hmm.
And we're going to be looking at Technical Volume 4
Okay.
of the IAEA report,
Okay.
which really focuses on that, radioactive fallout
Right.
and what impact it had on the environment.
Yeah, and what's incredible about this volume is just how detailed it is. The amount of analysis that went into it, it goes so far beyond just measuring contamination.
Right.
It's really trying to understand, like, the pathways,
Yeah.
long-term implications.
Right.
And, ultimately, all this information can be used to improve safety and preparedness for future events.
So it's almost like a scientific detective story,
Exactly.
piecing together these clues
Mm-hmm.
to kind of get this full picture of what happened.
Yep. And one of the first things the IAEA team did was to really meticulously map the fallout.
Okay.
When you think of that, you might think, oh, people are just walking around with Geiger counters.
Right.
But it's much more sophisticated.
Okay.
They used these aerial surveys,
Wow.
collected a ton of soil samples to create this detailed map of the contamination across the whole region.
And why was that mapping so important?
Well, imagine managing this complex situation
Right.
without understanding where the contamination was.
Yeah.
Or how severe it was. You wouldn't even know where to start.
Yeah, you'd just be throwing darts blindly. Right.
Exactly. These maps were crucial for everything.
Okay.
Evacuation zones to long-term cleanup.
So it's kind of like trying to navigate a maze without a map.
Exactly.
You'd be lost.
You'd just be wandering around.
Yeah. So what did these maps actually reveal?
Well,
Were there any, areas that were really hard hit?
oh, absolutely.
Oh, okay.
There was this one grid square they found in Okuma Town, just north of the plant.
Mhm.
They measured a whopping 15.5 megabecquerels per square meter of cesium-137.
Okay. So now I got to ask, because, I don't know off the top of my head,
Sure.
what does that actually mean? How bad is that?
So to give you some context, that is over 3,000 times higher than normal background radiation.
Wow.
Yeah.
Okay. I can definitely see why they needed to evacuate that area.
Right.
But what about the rest of the region? Was it pretty evenly spread out? Or
No, actually, and that's one of the key things that the mapping showed.
Okay.
The fallout pattern was very localized.
Okay.
And it varied significantly depending on things like wind direction, rainfall, the topography of the land,
So all these different factors were at play.
all these different factors. And this highlights, again, why that detailed mapping was so crucial, because a one-size-fits-all approach to cleanup
Right. Wouldn't have worked.
wouldn't have worked at all.
Yeah.
Yeah.
Okay. Let's maybe shift gears just a little bit and talk about food and water contamination. I think this is something that a lot of people are concerned about,
Yeah.
especially after a nuclear accident. So what did the IAEA report have to say about this?
Well, first off, Japan was very thorough
Okay.
in trying to ensure public safety when it came to food and water.
Right.
They analyzed over 500 types of food samples
Wow.
from all 47 prefectures,
Wow. They really took it seriously.
looking for signs of contamination.
So what did they find?
Well,
Were there any foods that were particularly concerning?
yeah, there were some initial concerns, especially with leafy green vegetables and milk.
Okay.
For example, in March 2011, the average concentration of iodine-131
Okay.
in leafy vegetables was about 3,800 becquerels per kilogram.
Okay. Again, I'm not a scientist.
Sure.
What does that number mean in terms of the actual risk?
Okay, so a becquerel is a measure of radioactivity.
Okay.
Basically, how many radioactive atoms are decaying per second. So 3,800 becquerels per kilogram means there were 3,800 radioactive decays happening every second in each kilogram of leafy greens.
Okay. That makes a little more sense now.
Yeah.
But is that dangerous?
Well, it depends on a lot of factors, including the type of radiation, how much is ingested, the person's age and health.
Right.
But to give you some context, the Japanese government set a regulatory limit of 2,000 becquerels per kilogram for iodine-131 in vegetables.
Okay.
So the levels they measured were definitely above the safety limits.
So what did they do about it?
They took action really quickly. They restricted the sale and consumption of those contaminated foods.
Okay, good.
And the good news is that combined with, the natural decay process,
Right.
the contamination levels dropped rapidly.
Okay.
By May 2011, the average concentration had fallen to just 5.6 becquerels per kilogram.
Wow.
So well below those safety limits.
Okay.
Yeah.
That's reassuring, at least.
Yeah.
It sounds like those interventions were effective
Yeah.
in protecting people.
Yeah.
But what about drinking water?
Yeah, that was also a concern.
Okay.
They monitored it closely, and restrictions were implemented in some places based on those iodine-131 levels.
Okay.
One example, specifically from the report, is Kawamata Town,
Right.
where restrictions for infants were lifted on March 22nd,
Oh, wow.
just a few weeks after the accident.
Yeah, that's interesting.
Yeah.
It sounds like, things were changing rapidly.
Right.
As they got more data, they were adjusting these restrictions.
Exactly. Yeah.
So we've talked about those local impacts, food and water.
Mm-hmm.
But the radioactive release didn't just stay in Japan.
Right? You're absolutely right. The IAEA report goes into the global impact of the Fukushima accident.
Yeah.
And it might surprise you how far-reaching the release actually was.
Okay, I'm intrigued. Tell me more.
Yeah. They use something called atmospheric transport modeling, which is basically like predicting weather patterns, but for radioactive particles.
Okay, interesting.
And this modeling actually revealed that the plume from Fukushima circled the whole globe.
Wow, that's incredible.
Yeah.
I mean, I knew that radiation could travel, but I didn't realize it could go that far.
Yeah, it really shows how connected our planet is.
Yeah.
And while the levels they detected in other countries were very, very low, didn't pose any real risk, the WHO, the World Health Organization, actually used that data to estimate worldwide radiation exposures. So it really shows how an event like this, even though it happened in one specific place, can really have these global implications.
Yeah, that's a sobering thought.
Yeah.
Okay. So we've talked about, the impacts on the land and how it's spread globally. But what about the ocean?
Right.
Obviously, Fukushima's right on the coast.
Yeah.
So I imagine there was some contamination there.
Absolutely. The ocean was a major pathway for release. And the IAEA report goes deep into the extent and nature of that contamination.
Okay.
They identified two main routes of contamination. Atmospheric deposition, which is basically where those particles fall from the sky into the ocean.
Okay, so fallout.
Right, fallout.
Yeah.
And then direct releases from the plant itself.
Okay, so a combination of both.
A combination, yeah.
Do we know how much radioactive material actually ended up in the ocean?
Yeah, the report estimates that somewhere between 1 and 6 petabecquerels of cesium-137 entered the Pacific Ocean.
Petabecquerels. Okay, I'm having flashbacks to high school chemistry right now.
Right.
Can you remind me, what is cesium-137?
Sure, so cesium-137.
And why is it important?
Right, yeah. So it's a radioactive isotope that's produced during nuclear fission, the process that powers nuclear reactors.
Right.
And it's particularly concerning because it's got a relatively long half-life of about 30 years,
Okay.
which means it takes 30 years for half of it to decay. And because it's chemically similar to potassium, it can be absorbed by living organisms, and it can build up in the food chain.
So if it has a long half-life and it can accumulate in the food chain, does that mean it could potentially pose a risk to marine life and even humans who are consuming seafood?
That's right.
Okay.
And that's why the IAEA and other organizations are very closely monitoring the levels of cesium-137 in the Pacific Ocean, particularly in things like fish and other seafood. The good news is the ocean is vast, so these things get diluted over time and distance.
Right.
While the immediate impact was significant, the long-term effects are more complex, and they require this ongoing monitoring and research.
So we're still learning about the ocean contamination.
Yeah.
And its potential long-term consequences.
Right.
Okay, so let's shift gears a little bit here.
Okay.
And I want to talk about radiation dose assessment. So the report mentions that the IAEA used a bunch of different methods to assess the radiation doses that people in the area received.
Yeah.
So can you walk me through what those methods were, what they revealed?
Yeah, they used a combination of things, environmental monitoring, personal dosimetry, and thyroid uptake measurements.
Okay.
So environmental monitoring, that's basically collecting samples of air, water, soil, vegetation to measure the radioactivity levels.
Right.
Personal dosimetry, that involves using these little devices that people wear to track their own personal exposure.
Okay, interesting.
And then thyroid uptake measurements are used to assess the amount of radioactive iodine that has accumulated in people's thyroid glands.
Okay, so like a multi-pronged approach to get this full picture of radiation exposure.
Exactly, yeah.
So what did those measurements tell us? Like, were people exposed to dangerous levels?
One of the main things they found was that the vast majority of people in Fukushima Prefecture actually received relatively low doses of radiation.
Okay.
In fact, the report says that 99.4% of residents received less than 3 millisieverts.
Okay, now, millisieverts. Remind me what a millisievert is.
Sure.
And how it relates to actual health risks.
Okay, so a millisievert is a unit of measure for the biological effects of ionizing radiation.
Okay.
And the average person actually receives about 2 to 3 millisieverts of radiation per year from natural sources.
Oh, wow.
Like cosmic rays, radon gas, stuff like that.
Okay.
So the doses received by most people in Fukushima, while higher than normal, were still within the range of what we experience every day.
Okay. That makes you feel a little better.
Yeah.
But what about the people who did receive those higher doses?
Right.
Were there any long-term consequences?
Well, that's where it gets a little more tricky.
Okay.
While we know that high doses can cause acute health effects,
Right.
like radiation sickness, the long-term risks associated with low doses are less clear.
Okay.
The report acknowledges that there are uncertainties associated with these dose assessments, especially in complex situations like this.
Right.
And it highlights the need for ongoing monitoring and research to better understand those potential impacts.
So it's kind of a wait-and-see approach.
Kind of, yeah. But they are actively tracking this information to learn as much as they can.
Good. So we talked about people, but what about plants and animals?
Yeah.
I'm curious to know, how did the fallout affect those surrounding ecosystems?
Yeah, that's a good question. And it's another area the report really goes into.
Mm-hmm.
They studied how various species were affected.
Okay.
And they found some really remarkable stuff.
Oh, okay.
For example, they found that dose rates for bamboo and grass near the plant reached 1 to 2 milligrays per day.
Okay, milligrays. Now, another unit of measurement.
Right.
Got to refresh my memory on. What's a milligray, and how does that relate to radiation exposure?
Okay, so a milligray is a unit of absorbed dose,
Okay.
which measures the amount of energy deposited by radiation in a given material.
Mm-hmm.
It's related to the sievert, which we talked about earlier, but it doesn't directly translate to the biological effects.
Okay.
However, those dose rates for the bamboo and grass, they're significant, indicating those plants were exposed to a lot of radiation.
Wow. I hadn't really considered the immediate impact on plant life.
Yeah.
So did they see any, immediate effects on those plants and animals?
They did observe some effects.
Okay.
Things like increased mutation rates in certain plants.
Wow.
Changes in the behavior of some animals.
Interesting.
But the long-term ecological consequences, they're still being studied.
Right.
And these studies are important for understanding how radiation moves through food webs, how ecosystems recover, and what steps we can take to mitigate those impacts in the future.
Right. So it's, again, this kind of giant unplanned experiment that we're still learning from.
Yeah, exactly.
Okay. So we've talked about, mapping the fallout, assessing the doses, both for humans and in the environment.
Mm-hmm.
But what I'm curious about is, how does all this data connect back to the bigger picture?
Yeah.
What does it actually tell us about the accident itself?
That's a great question.
Yeah.
And that's where the real value of this technical volume is. Okay.
By meticulously analyzing the fallout, the IAEA experts could piece together a more complete understanding of what happened during those first few days of the accident.
So like a forensic investigation.
Exactly.
But on a massive scale.
Right, yeah. And one of the key things they were able to determine was the timing and magnitude of those radioactive releases.
Okay.
By analyzing the composition and the distribution of the fallout, they could estimate when and how much radioactive material was released from each reactor.
Wow.
Yeah.
That must have been an incredibly complex process.
Oh, it was. It was
Yeah.
a monumental task.
Yeah.
No doubt about it. But the IAEA, they brought together a team of experts from all over the world,
Right.
each with their own specialized knowledge.
Right.
And they used these very sophisticated computer models
Wow.
combined with that real-world data
Yeah, okay.
to create this detailed reconstruction of the releases.
Wow, that's amazing. So what did they find? Were there any surprises? Well, one of the most significant findings was that most of the radioactive releases happened in those first few days after the earthquake and tsunami.
Okay, so that's consistent with the timeline of events we talked about.
Exactly.
Especially those hydrogen explosions that damaged those buildings.
Yeah.
And kind of compromised those containment structures.
Exactly.
Yeah, because those explosions would have, created a way for that material to escape.
Exactly.
Okay.
And by analyzing those specific isotopes in the fallout, they could identify the different sources of the releases.
So they could trace the material back to its origin?
Essentially, yeah.
Wow.
And this level of detail is so crucial for understanding the severity of the accident.
Right.
And the risks posed by the different types of radioactive material.
Right.
And it helps inform decisions about long-term stuff like remediation, waste management.
So it's like they're creating a fingerprint of the accident, which is fascinating but also a little terrifying.
I understand that. It's amazing to see how science can unravel these things.
Yeah.
But it's also a stark reminder of what can happen.
Right. So we've talked about the timing and the magnitude of these releases, but what about the direction?
Yeah.
The report mentions that wind played a big role in how the fallout was dispersed.
Wind patterns are crucial.
Okay.
They determine the path of this airborne radioactive material.
Right.
And in the case of Fukushima, the wind carried a large portion of that release out over the Pacific.
Okay, so that explains why we see higher contamination levels in the ocean.
Yeah.
But lower levels further inland.
That's a big part of it, yeah.
Okay.
But it's important to remember that some material did travel inland.
Right.
And those localized hotspots, like that one in Akuma Town,
right,
they required their own attention.
Okay.
In terms of evacuation and cleanup.
It's amazing how, something like wind direction can have such a big impact on something like this.
It's a reminder that these accidents are not isolated events.
Right.
They're influenced by all these complex factors, both human-made and natural.
Right.
And understanding those interactions is crucial for developing good strategies, whether it's prevention, preparedness, response.
Okay. So we've talked about a lot of technical details, but what about the human side?
Yeah.
How did all this data actually impact people's lives?
That's a really important point.
Yeah.
And it's where the science intersects with the real-world consequences.
Right.
The data helped inform decisions about evacuation zones, food restrictions, long-term health monitoring.
Okay.
And it also played a role in how the public perceived the accident.
Right. So it wasn't just about the numbers.
Exactly.
It was about using those numbers to make decisions that actually affected people.
Exactly, yeah.
And those decisions must have been difficult.
Oh, they were.
Right.
Yeah.
Trying to balance protecting public health while also minimizing disruption.
Right.
And allowing people to go back to their lives.
Exactly.
I can only imagine how stressful and uncertain that must have been for those communities.
It was an incredibly challenging time.
Yeah.
And the IAEA report, it actually acknowledges the psychological and social impacts of the accident.
Right. Which are just as important.
It's just as important, yeah.
It's a reminder that these accidents are not just technical events.
Right.
They're human tragedies.
Yeah.
With lasting impacts on individuals, families, entire communities.
Exactly.
And that human dimension, I think, is something we really have to keep in mind.
Yeah.
Okay, so we've delved into the fallout, global impacts, how it affected humans, the environment, but we're not done yet.
We're not done.
There's one more piece of this puzzle.
Right.
The long-term consequences.
Right.
And that's what we'll be talking about in the final part of this episode.
Absolutely.
Yeah, it feels like we've just scratched the surface of all this.
Wow.
This is incredibly complex. So where do we even go from here? What are those long-term consequences that we need to think about?
That is the question, isn't it? And it's something that the IAEA report really grapples with.
Okay.
The long-term consequences of Fukushima are so multifaceted.
Yeah.
And they're going to continue to unfold for decades, maybe even centuries.
Wow. Okay, so we're talking about impacts that go way beyond just that immediate aftermath.
Oh, yeah.
So what are some of those key areas?
Well, one of the most pressing concerns is the long-term health impacts.
Oh, okay.
Particularly cancer.
Right.
We know that exposure to radiation increases the risk of developing certain cancers.
Right.
But quantifying that risk, especially at those low doses that most people received in Fukushima, it's really hard.
So it's not a simple cause and effect.
No.
Like you get this much radiation, you automatically get cancer.
Right. It's not that simple.
Right.
It's this mix of things.
Yeah.
Genetics, lifestyle, the type of radiation, how much.
Right.
But even though that individual risk might be low, when you're talking about a large population, even a small increase in cancer rates can be a lot of people.
That's a good point, yeah.
Yeah.
So how are they addressing this uncertainty? Is there any way to, like, track those potential health impacts over time?
Yeah, thankfully there is. The report highlights how important these long-term health monitoring programs are.
Okay.
They're key for tracking those trends and looking for any significant increases in cancer or other issues that might be linked to radiation exposure.
So it's about collecting that data over time.
Exactly.
Seeing if any patterns emerge.
Exactly. And these programs aren't just limited to cancer.
Right.
They're also looking for things like cardiovascular disease,
Okay.
thyroid disorders, even mental health issues related to the stress and trauma of the accident.
Of course.
Yeah.
So it's really this holistic approach
It is.
to understanding how this affected people's lives.
Absolutely.
But health isn't the only concern.
No, it's not.
What about the environmental legacy?
Right? That's just as complex and far-reaching.
Right. We talked about the ocean contamination.
Yeah.
But those effects on the ecosystems are still playing out.
They are.
So researchers are looking at how that radiation is moving through the food web, how it's affecting different species, and how those ecosystems will actually recover.
Exactly. It's like this giant unplanned experiment,
Right.
and we're still trying to understand it.
Yeah. Are there any signs of recovery yet?
It's a mixed bag.
Okay.
Some species are definitely more resilient than others.
Right.
And there is evidence that some areas are starting to bounce back.
Okay.
But in other places, those impacts are sticking around.
Yeah.
And it could be decades before we see full recovery.
Wow. Okay, so it's a reminder that these consequences can last for generations.
Right.
And speaking of long-term challenges, the report talks about this massive undertaking of remediation.
It is huge.
Can you explain what that actually involves?
Sure, remediation basically means cleaning up the mess.
Right.
But when we're talking about a nuclear accident, it's not easy.
Right. It's not like just wiping down a counter.
No.
Hey.
It's a huge range of activities.
Yeah.
All aimed at reducing those contamination levels.
Okay.
So that can include removing contaminated soil, vegetation, decontaminating buildings, infrastructure, treating the water.
It sounds like a lot.
It is a lot.
Yeah.
It's like trying to put Humpty Dumpty back together again.
Right. Exactly.
But on a massive scale.
And are we even going to be able to put all the pieces back together?
That's a good question. And like with Humpty Dumpty, there are probably going to be pieces that can't be fully restored.
Right.
Some areas may just stay contaminated.
Yeah.
For decades, maybe centuries.
Oh, yeah.
Requiring constant monitoring and restrictions.
It's humbling to think that we can't just erase the consequences of what happened.
Yeah.
Especially when we're talking about something as powerful as nuclear energy. So where do we go from here? What are the big takeaways from Fukushima? And how do we use those lessons to prevent something like this from happening again?
That's the most important question.
Yeah.
And the IAEA report addresses it.
Okay.
They highlight some really crucial lessons, emphasizing that Fukushima wasn't just a one-time thing.
Right.
It was a wake-up call
Okay.
for the whole industry.
So what were some of those key lessons?
Well, one of the most fundamental takeaways is just how important those safety measures are.
Okay.
Fukushima showed us that these plants need to be designed and built to withstand even the most extreme events.
Okay.
Whether it's a massive earthquake, a tsunami, or something we haven't even thought of yet.
Right. Like we got to think about the unexpected
We do.
and plan for that.
Absolutely. And it's not just about physical safeguards.
Okay.
Like stronger containment structures or backup power.
Right.
It's also about those organizational structures.
Like that.
Clear lines of responsibility and a safety culture. That goes through every level.
Right. So everyone's on the same page.
Everyone's on the same page, yeah.
Okay.
From the operators to the regulator.
Right. So creating that culture where everyone feels empowered to speak up
Exactly.
if they see something wrong.
Absolutely.
Safety is the priority.
It has to be.
Yeah. Another crucial lesson that the report highlights is communication,
Yes.
both during an emergency and in the aftermath.
Right.
Fukushima showed us how hard it is to get accurate information to people,
It really did.
especially when everything is changing so fast.
Yeah, it's a tough situation.
So what can we do to improve that communication?
Well, transparency and honesty are key.
Okay.
People need to know they're getting the truth,
Right.
even if it's not what they want to hear.
Yeah.
And it's not just about the facts. It's
Oh.
about acknowledging what we don't know.
Right. Being upfront about those uncertainties.
Exactly. It's about building that trust.
Right. Because that's so important.
It is.
Especially when people are scared. Okay. And then finally, the accident showed us how important international cooperation is.
Yeah, it really did.
Fukushima wasn't just a Japanese problem.
Right.
It was a global event
It was.
that needed a global response.
Exactly.
It shows how connected the nuclear industry is.
Yeah.
And that countries need to work together.
They do.
Share what they know.
Action.
Share their expertise.
Absolutely.
The IAEA, they played a big role in coordinating that response.
They did.
And they continue to work with countries all over the world
They do.
to make things safer,
Right.
to share those lessons learned and develop those best practices.
Absolutely.
Well, this has been incredibly eye-opening.
Yeah, it's a lot to take in.
We've covered so much,
We have.
from the technical stuff to the impacts on people on the planet.
Mm-hmm.
But I think the biggest takeaway for me
Yeah.
is that we need to learn from this
Absolutely.
and work together to make sure it never happens again.
I agree.
Thanks for joining us.
It was my pleasure.
And to our listeners, we encourage you to keep learning about this.
Yeah, keep asking questions.
Challenge those assumptions and be part of the conversation about the future of nuclear energy.
Absolutely.
Until next time, keep diving deep.